put that up to record. Okay.
Alright, class, let me start it. We're trying something new with the recording today. Hopefully this will be better than last week. Quick announcement before we start. There's homework 5 that's available on Canvas. I know that many of you started working on it already. It's going to be quite somewhat more heavy on implementation than your previous homeworks. So I encourage you to start soon. On the other hand, those of you who already started this would realize that it's not too much of a change from your perceptron homework and your decision trees homework. So if you have any trouble, if you had trouble with the previous homeworks, then this is a chance for you to kind of reset and restart. Any questions about homework 6 or 5? 5, yeah. Oh, there were some minor edits to that homework. I uploaded a new version on Canvas recently. Basically, there's one less hyperparameter for you to try for your SVMs. Otherwise, any questions? Is there a question? All right. If there are no questions and if you haven't yet started, I encourage you to start soon because, like I said, this could take a bit of time for running things and things could get crowded because, as the second point says, the end of the semester is coming up and deadlines tend to crowd up. One thing that at least you have two things to keep in mind. Your class projects, they due, the final reports and everything is due on December 14th. Originally, the website said 15th, but I had to change it because it turns out the last exam day is the 14th. And I'm not sure if I'm allowed to have you submit anything after that. So, in fairness to you and for any travel plans you may have made, it has to be the 14th. So for your projects, you need to submit a short report on Canvas and also submit your code. Some of you I know cannot submit your code because of different sorts of constraints that you may have. Like for example, if your project is inside some organization and your code is not public and so on. So in that case, come talk to me and we can figure it out. Almost all of you are not in that position, so you'll end up submitting your code. Please don't submit your data. I don't want to get emails from Canvas saying that we broke it. The other deadline that's coming, not a deadline, but other event to keep track of is your final exam. It's on December 14th, and I'm sure you're excited to notice it's at 8 a.m. So if you know, what can I say? It's at 8 a.m. It hurts me as much as it hurts you. It's in class. No, the same rules as the midterm. No, what do you call it? No notes and such things. We'll cover everything from and including computational learning theory. So there's a mild overlap with the midterm, but not too much. But all said and done, it's impossible not to touch things that we saw before the midterm, like the idea of overfitting. I might ask you something about overfitting, and I might have spoken about it during decision trees, but you can't have a machine learning final without talking about overfitting. But largely we'll cover things that start with learning theory. Any questions about any of these things? Homeworks and exams and projects and all these good stuff? Yes?
So the code for our final projects, lots of things that all of us that along the way is like, oh, here we'll change this in the code, and then we'll come out this line. Do you want our code to run the whole thing and then output that?
So what I would like your code is good question. So you're talking about the Kaggle thing? Yes. So for Kaggle, the document on Canvas says you're expected to have 6 submissions, right? Of course, you're not required to have only 6 submissions. You can do 1 million if you want, but you should tag 6 of those submissions as these are the official ones. And I want your code to reflect those 6. Just make sure that stuff is uncommented and it actually runs. Yeah. Other questions? I'll be talking a bit more about the projects as we go along. But really, most of the information is on the class website, so you should not have too many concerns about this. And we've spoken about this in the past many times. Any questions about the final? So please keep note of the time. It's not the usual class time, it's its own thing, so make sure you set an alarm or something. Alright, another announcement is about this event today, the Data Science Club. I mentioned this last week. It's a student club, so maybe many of you are a part of it. There is this talk today at CSC. I don't know where the building is. I'm sure you all know where it is. It's about how to store and manage large amounts of data. It's sponsored by Goldman Sachs. It's this evening, 4:30. Kind of overlaps with office hours, but take your pick. Okay. All right. If there are no logistical things, let's go to logistic regression. We're going to continue where we left off. So I want to just very briefly mention logistic regression and revisit an idea that we've encountered before. namely learning as loss minimization, because that becomes important once we come to neural networks, which we'll start today. So in the last lecture, at the very end of the last lecture, we looked at the logistic regression classifier, and we looked at how we can train maximum a posteriori, use the maximum a posteriori criterion for training a logistic regression classifier. And you work through the math, you take log and you just rearrange all the stuff. And it turns out it takes a rather familiar forms. The classifier, which we started off with all this grand probabilistic intentions, ends up being a linear classifier that we obtain by minimizing the sum of what we can call the logistic loss, which is this term here, and another term which is the norm of the weights, which is really the regularizer. Of course, we did not call it a regularizer. When we came up with this term, we called it a prior. We said, in the absence of any other information, we want our weights to be centered at 0, with or weights to be drawn from every weight to be drawn from a normal distribution that has mean 0 and standard deviation sigma, and you just work through the algebra and you get something like this. So yes?
That log doesn't include the last term, correct?
That log doesn't include the last term, which means there's a bracket missing, yes. Oh, you're the first person to ever see this. Yes. So, wow, yeah, okay, good. At least somebody balances brackets. So, what we have here is the sum of a term that depends on the data, the first term, and we can call that the loss function. In fact, we will call that loss function, that's the logistic loss. It essentially can be seen as a term that penalizes mistakes. It penalizes models, in this case W's, which make mistakes. And how do we define mistake? We define the model to be, or how do we penalize mistake? We say a penalty is more when this term is more. The second term is the somewhat interesting thing here. It's a regularizer. We've seen this regularizer before. This is essentially the same thing that we had for support vector machines. But of course, we did not. When we looked at support vector machines, we invented this term by looking at this theorem from Wapnick and said, we need to maximize the margin. Maximizing the margin naturally leads to minimizing the norm of the weight, blah, blah, blah. So we got the norm of the weight as a regularizer. Now, in logistic regression, we have no such things. We said we started off the story in a completely different way. We say that we have this prior. In the absence of any data, we believe something about the weights. And that particular belief manifests itself as this regularizer. One way or another, you end up at something that looks very similar. And this is a higher level, almost philosophical point, right? I mean, if we come up with something that, the same idea that appears in through multiple different intellectual lineages is probably something that is fundamentally true. And this is a nice convergence of ideas. Your first homework, I'm not going to talk about how to solve this problem, how to optimize this problem, because that's your homework question. The first homework question is basically asking you to invent a stochastic gradient descent algorithm for this. We've seen that before. We've seen that in SVMs. We've gone through the details of it. So I would like you to kind of go through that process all over from the beginning. Historically, it turns out, just a matter of historical interest, it turns out that stochastic gradient descent was not used for logistic regression. I don't know why, but other optimization schemes, in particular something called LBFGS, which is, the abbreviation is amazing. It's Limited Memory Broyden Fletcher Goldfarb-Shano. You're not going to remember that. Anyway, it's an algorithm for optimizing these kinds of things, and it was used quite a bit, and graduate students spent a lot of time implementing it and pulling their hair out. It turns out SGD is much, much simpler, and which is what you will implement in your homework. Right. So I'm going to step up a bit just to kind of quickly wrap up logistic regression. Logistic regression is an interesting mix of a lot of ideas we've encountered before in the semester. It's a classifier. It's a probabilistic model, meaning that it's a classifier that predicts a probability for whether the label is true or false. It's a discriminative classifier, which means in order to build this model, we optimize, or rather, the classifier itself predicts the probability of the label condition on the input. We never ever model P of x comma y, which is what we did in the naive Bayes. But what we saw in the last lecture is that the naive Bayes classifier and the logistic regression classifier take a similar functional form for the posterior probability P of y given x. It's a discriminative classifier that can be trained probabilistically in a Bayesian way. What that means is you can choose to optimize the likelihood, so you get the maximum likelihood estimate, or you can choose to optimize the posterior probability, in which case you get the maximum a posteriori classifier. Each of these gives a slightly different objective function. Basically, what we have is the first one, map, has a regularizer, the second one does not have a regularizer. But I've already talked about regularizer. Another way of thinking about it is you could give up all pretense of being a Bayesian. You say, I woke up one morning and I dreamed of the logistic loss, and I'm going to optimize it because that's what feels right today. So you can think of it as a discriminative classifier that optimizes the logistic loss. All of these things are the same thing. It's the logistic regression classifier. Oh, it's also a linear classifier. I should not forget that. So, any questions about logistic regression? This is almost like a summary of the last lecture. So, if there are no questions, I assume that, like I always do, one of two things: all of you understand it, or none of you understand it. Thankfully, your homework will force you to kind of get into the details of this. So you have another opportunity to encounter these ideas. All right, let me move a little bit, revisit an idea we've encountered at least once or twice before, which is learning as loss minimization. And the reason I want to revisit it is because this gives us a template for essentially inventing learning algorithms. This is the dominant template for inventing learning algorithms today. Today, if you want to invent an algorithm, a learning algorithm, you're not going to start from scratch like ID3, for example, for decision trees. Most often, what you would do is you would try to optimize the loss function. So the setup is you have examples, x's, you assume that examples are drawn from a fixed, possibly unknown distribution, D. And there is an oracle classifier, which you don't have access to, but you'd like to mimic. And this classifier, let's call it F. What F does is it labels all the examples that you have. And so you have a data set. But what you care about is not to optimize find the best classifier on your training set. What you would like is to find a classifier, let's call that H, that explores the entire hypothesis space and finds the one that minimizes the expected loss, because that's a sign of generalization. The expectation is over this unknown distribution that we don't have access to. Instead, we approximate that expectation using the data that we have. We approximate it as this average loss or the empirical loss on the training set. So the goal of learning is to minimize the empirical loss on the training set. We've seen this idea multiple times. Of course, this is not good. I can always minimize empirical loss on the training set and get a classifier that has zero empirical loss. How would I do that? What could happen? Why would I get a zero empirical loss? What? You overfit. A classifier that remembers the entire training set gets zero loss for the training set, because you just memorize the entire data, you put it in a database, and every time a new example comes up, you look up the label. Of course, it's perfect and it's useless. So what we need to do is we need to penalize. We need to somehow account for generalization. And the almost philosophical point that we keep encountering is that complexity is a bad thing unless it's needed. So we need to change this optimization problem to somehow penalize complexity. And the term that penalizes complexity, as we've seen before, is a regularizer. So we don't really just minimize the loss function, we minimize the sum of the regularizer and the empirical loss. So this is regularized risk minimization or regularized loss minimization. If you have a linear classifier, your classifier, the H, is completely defined by a set of weights, W. So the regularizer is just, there are many possibilities of, there are many regularizers you can use. Perhaps the most common one is the L2 norm. And we've essentially invented this in two different ways. So you get L2 regularization plus some loss. Now, notice that the loss is completely defined by the input, the true label, yi is the true label, which is really f of xi, and the classifier w. Okay, let's talk about this loss. The loss is something that should penalize mistakes. What's the loss function that you should really be minimizing? What's the ideal loss function if you care about minimizing mistakes? You don't have to name it. You can tell me what you do. Yes?
Minimize error.
You minimize error. Exactly. You go over your training set. You count how many times the classifier makes a mistake. Add up the number of mistakes. That sum, you would like to minimize that. That particular thing is called the 0-1 loss. You minimize classification mistakes. The 0-1 loss, basically, you can think of it as the number of points that are deducted for mistakes. You lose a point, or your classifier loses a point. If it makes a mistake, it doesn't lose anything if it does not make a mistake. For a linear classifier, of course, we can say that a mistake is said to happen when y w transpose x is negative. So really, the 0-1 loss is the sign of y w transpose x, but negated. So it is -1 or something like that. If it's -1, if y w transpose x is less than 0, then 1 point is lost. Otherwise, no points are lost. That's nice. That's what we would like to do, but tough luck. This is an intractable problem. We don't know how to solve it, but it's intractable. It can be hard, which means that we need surrogates. We need to approximate the 0-1 loss using some softer notion of mistakes, and that's really the whole cottage industry here. There are many approximations of this. We've seen all of these in class so far. We would like to minimize the 0-1 loss, but instead we invent this approximation called the perceptron loss, and that gives us the perceptron loss. Instead, we invent a surrogate called the SV hinge loss, and that gives us the SVM. One perspective of AdaBoost is that you're minimizing the exponential loss, or maybe you want to minimize the log loss or the logistic loss, and that gives us logistic regression. All of these are essentially different surrogates for the 0-1 loss for classification. This becomes important once we come to neural networks, because even there we will invent a loss function for classification. It doesn't matter that your classifier is linear or anything else. You can always write down a function of this kind. If you are the kind who likes to see pictures instead of equations, the 0-1 loss is what we would like to minimize. The horizontal axis is y w transpose x. The vertical axis is loss. So what we have here is, on this side, y w transpose x is positive, which means the sign of y and w transpose x is the same. So the classifier is correct. So it should not be penalized according to 0-1 loss, and that's what we have. The penalty is 0 here. Otherwise, there should be a penalty of exactly 1. 1 there. So you have a penalty. We've seen this before. The hinge loss is an approximation of this that says, you know what? Yeah, it's fine that there are no mistakes on this side, but in addition to penalizing mistakes, I don't want things to lie too close to the hyperplane, too close to the the separator. So I want to penalize classifiers that put points within the margin. So I have a penalty that keeps growing even on correct classifications that are in the margin, and it keeps growing as the mistake gets worse in some sense. Then you have the perceptron loss, which does not have a margin. It just says it agrees perfectly with the 0-1 loss on this side, and the mistake, as the mistake grows, the loss grows. And I have left it as an exercise in the past. If you've not done that, I want you to do it for real. Take the perceptron loss, minimize it, implement, or on paper, derive the stochastic gradient descent algorithm, and convince yourself it's the same perceptron algorithm that we saw many weeks ago. And then there's the exponential loss. AdaBoost basically minimizes something called the exponential loss, and this is a very, very cool unification of a lot of ideas. The log loss is what logistic regression minimizes, and notice that the log loss is very interesting. Not only it penalizes, actually also the exponential loss. It penalizes. It has a penalty at all points, even if the classification is correct. There is a penalty, and that penalty keeps shrinking as the classification gets more and more correct. So what this says is that the log loss and the exponential loss are never zero. They are basically zero only at YW transpose X equals infinity. Any questions?
So the log loss keeps decreasing no matter what.
The log loss keeps decreasing. Say that again, sorry.
Since it doesn't go to zero,
Yes.
it keeps decreasing. Like there's no absolute minimum.
There is no absolute. It is a convex function. It does have a minimum because you're looking at the sum of many of these things, and they could kind of contradict each other. So that's an interesting point, but you're adding up some minimum that's not zero. The minimum is never zero because that's right. The minimum is not going to be zero. Yes. Yeah.
In a way, since there's always a loss involved, if we didn't regularize it, then those two functions would break, right?
Not quite. There is a minimum. It just so happens that the minimum is not zero. It's the same answer as the previous one. So keep in mind that you're minimizing a term. So this is for one example. This is the loss for one example. What we want to minimize is the sum of L. The sum is going to have a minimum because it's a convex function. The minimum does not have to be negative infinity. Is it actually going to be negative infinity? It might. It could be negative infinity. But it doesn't have to be because you could have data that is not perfectly consistent with, it's not linearly separable, which means you might actually end up getting two curves that essentially contradict each other. And so you could get something that is not in negative infinity. However, adding a regularizer in some sense is always an important thing because it smooths out what you have. It smooths out the optimization problem. It essentially conditions it to be a better one. So I would suggest you never not add a regularizer, or let me say that better. You always add a regularizer because you do want the regularizer is more than just a conditioning of the optimizer, but it's also it gives you generalization. Always add regularization. Now, one question that always comes up, and I think it did come up at after class last week or something. You have so many loss functions and so many of these things, and which one should I pick? Is there a reason for me to use logistic regression? They look so different, right? So what I thought is I could show you a picture of the same thing zoomed out, or zoomed out even more. Basically, they end up having a similar sort of an effect. Perceptron and SVM basically are indistinguishable. The fact that these things don't go to, I removed exponential loss because that basically just goes out of the screen. The fact that there is no zero here does not really matter because when you zoom out enough, everything is zero. And what you have is either something that is, they're both almost linear. And if you take the slope of the SVM and halve it, you basically get logistic regression. So what they end up doing is they end up performing roughly equivalent. So what I do in practice is I use whatever classifier I have the code for. If my data is in a format that fits some code, I just use it. And hopefully in your project and your homeworks, you will come to a similar sort of a conclusion. In practice, what I've found is a regularized logistic regression, SVM, which of course has regularization, and average perceptron. All three of these, if you tune them well, Meaning, if you find the best hyperparameters for each of these, they tend to be roughly similar. So there's not much to decide which one to pick. Yeah.
This is kind of what we would expect though, right? All of these are finding for us a linear classifier. So the linear classifier that they find should be roughly equivalent.
Yes and no. Yes, because you want them to find linear for the reason that you just said. However, maybe there is, keep in mind, each of these loss functions is expressing a preference on the hypothesis space. Essentially, you can think of it as saying, among all classifiers that are equally good, I prefer the one that has a lower loss. Now, maybe one of these criteria is truly a better one. For example, I could invent a loss function that's lousy. So here's a loss function that's lousy. It's say 0 everywhere here because you want it to be that way, and it's 0 everywhere here. Or even worse, I want a loss function that's 0 everywhere on this side and goes this way. Now, not every loss function needs to be identical. There's no reason that they should be. It's just a happy accident. And again, like I said, a convergence of these ideas of preferring simplicity that suggests that all of these tend to be good. But keep in mind that there are bad loss functions. These are not used. Most functions are bad loss functions. But yeah, that's an interesting point. Most reasonable loss functions would be roughly the same. All right. Are there any other questions about learning with minimizing losses? You should have seen this before and you should be somewhat comfortable with this. If there are no questions, we're going to start with neural networks. And I have to make there's a huge caveat before I start. Neural networks are a very fast growing, extremely wildly moving target when it comes to space of ideas. And what I'm going to provide in today's class and to these ideas, and I'm going to talk about some core machine learning ideas that seem to pervade across a lot of neural networks. In particular, I won't be talking about any specific neural network architecture. Hopefully, you'll know what that means in the next 10 minutes, or any, the latest and the greatest papers that you may hear about. But I'll give you the tools that you might need to kind of think about those papers. So to start off, let's just step back up and see where we are and talk about what are some questions that we've completely sidestepped in this semester. We've looked at many different learning algorithms. We've looked at decision trees, perceptron, logistic regression, SVMs, boosting, naive Bayes. I'm sure I'm missing a few. But across all of these, really, we looked at a whole bunch of general machine learning ideas. We have been talking about overfitting a lot. When we talked about perceptron, we looked at the idea of learning by minimizing or bounding the number of mistakes. Then we spent a fair bit of time on the pack theory and sample complexity and such ideas, which gave us the tools that we need in order to build learning algorithms. It gives us the language to talk about minimizing loss and such things. And then we looked at VC dimensions and such ideas, which kind of generalizes this to a whole bunch of pretty much most models that we can think of. And the key idea that we kept encountering is that it's not enough to minimize training error. Training error is easy to minimize. What we care about, the goal of machine learning, is generalization. And that leads to empirical loss minimization. And then we took a completely different, we went in a completely different direction, or so it seemed, when we started Bayesian learning, which gave us a third criterion to talk about learning. First, we looked at mistake bounds, then we looked at pack, and then we went to Bayesian learning. So it gives us another way of asking, what does it mean to learn? Across all of these things, we explored these different algorithms. Now, it turns out many of these algorithms that we looked at are essentially linear in the features. AdaBoost can also be seen as linear if you think of the weak classifiers as your features. What we did not address at all, or what we did not really resolve, is what if I want to train nonlinear classifiers? And the answer that I have given when asked so far is basically a cop-out. What you do is you invent nonlinear features. You do some feature transformations that are nonlinear. We did not talk about kernels, unfortunately, but that's another way to think about nonlinear features. And maybe if I had another week, we would be talking about kernels. Also, another question that we don't really talk about is where do features come from? In all your homeworks, I have conveniently given you featureized data, right? I mean, I've given you features and you train models. Some of you in your class projects, the exploratory ones, for example, you've had to deal with feature design and feature invention, and I've had at least one person talk to me about how that seems to be taking up most of the time. In your competitive project, of course, you have the freedom to invent your own features, and I know that at least some of you are doing that. But where do these features come from? It's a question that's not really addressed, and rightfully so, because maybe features need to encode inherent domain knowledge about the system that you have. Maybe you want to get features from maybe you're a physicist studying neutrinos, and you know something about neutrinos that you cannot just learn from data, so you might want to encode them as features. So we've always left it as domain expertise. It turns out that this idea of learning representations or learning features is one way of thinking about neural networks, and in my opinion, it's like a core idea that seems to be pervasive. So in today's and Thursday's lecture, we'll be looking at what neural networks are. They are a family of hypothesis classes. It's not just one hypothesis class. They are a family of hypothesis classes. Anytime you encounter a new hypothesis class, you need to ask yourself two questions. How does it work? Meaning, how do you make predictions with it? And the second question is, how do you train with it? If you can answer these two questions, and if both these answers are computationally reasonable, then you have something interesting. Of course, you also need the hypothesis class to be expressive enough. So there are three criteria. So we'll talk about prediction first, and then we'll talk about training. When we talk about training, we'll get to the famous backpropagation algorithm. And then we'll get into some practical concerns. It turns out the list of practical concerns for neural networks is so large that it can be an entire semester of its own. Unfortunately, I'll talk about it for maybe 15 minutes. And I can give you pointers for where you can see more. Oh, but that reminds me also, it turns out that next semester, so one question that also comes up is, where do we go next? Next semester, there will be a few classes on neural networks. I'm teaching a class on neural networks for NLP. Tolga Tassisen from ECE is going to teach a class on neural networks for computer vision. So if these things are interesting to you, you should see if you can get into those classes. All right, let's talk about what neural networks are. We'll talk about what the hypothesis class is, and then we'll talk about what the general form of the hypothesis class is, and then we'll talk about the expressiveness of these classes of functions. You've seen linear classifiers. Here's a cartoon way of looking at a linear classifier. You have inputs. These are the x's. These are the features. The way to interpret this diagram is you have these wires that carry information along this, and when x1 moves to the wire, it gets multiplied with w1. So here you get w1, x1, and so on. And then all of them are added up. That's the summation unit. And so what you have there, what you have right here is a dot product. This is just another way of thinking about a dot product, if you prefer this. And then that is pushed into another operation, namely the thresholding operation. So what you get here is the sign of the dot product of the input with the weights. It's just another way of putting it. The reason this is interesting is because this kind of a graph is called a computation graph, where nodes are basically some sort of processing of the inputs that come in, and the edges carry information, and the edges are weighted, and anytime information flows along the edge, it gets multiplied with the weight. This is like a very simple kind of a computation graph, and this is a class of functions. Of course, we've never seen this sort of computation graph picture before. The reason is I personally feel more comfortable just looking at the math, but I know that's not always true. But with just this simple sort of a classifier, we've seen different learning algorithms. We've seen perceptron, SVM, logistic regression, and so on. And really, all of these can be unified under the theme of minimizing loss. Now, one question that comes up is, where do these features come in? I mean, all of these things here, how do I know what they are? And an intriguing idea is the following. Maybe I don't need to invent features. Maybe I can leave that job to a classifier. Maybe a classifier can invent features for me. So let's try that. What we do is we have this computation graph, we have this thing here, and let's separate the decision part of it, which is really all of this stuff, from the features, which is this stuff. So let's separate it out. And W1 does not directly act on the first feature. Instead, W1 acts on some decision of another classifier. What does that classifier look like? It's a computation graph. It does not necessarily have to have the exact shape, but then, who's going to draw all of that stuff again? So it's just another classifier. Similarly, the second W2 also gets the input from another classifier, and you get the final part of the inputs to the classifier itself comes from another whole bunch of classifiers, in this case 4 classifiers. Yes, first you and then Robert. Yeah.
Okay, so the dot product for W2,
Yes.
is that,
So are you talking about this one here, the one that's
yeah, so it seems like in your first dot product, you included all of the features, the X features.
yes,
And then in the second dot product, are you doing that as well?
yes.
So is it the threshold that changes?
No,
Or
what
is it the
changes
same?
is the weight.
Okay,
So the only thing that's different between these things is the weight. So maybe this one has weights W1, let's not use W's again. Let's just use numbers, okay? Maybe the top thing has weights of 1, 2, 3, and 4, and this one has maybe -1, 3, whatever. It's a different model. It's a different classifier if you want to think about it. It's a different classifier, and as we will see later, there's tremendous flexibility that is that gets opened up once you start thinking in terms of these computation graphs, because everything is up for grabs. Yes.
Isn't this just ensembling?
It is an ensemble. In fact, another way of thinking about a neural network is it's a learned ensemble. That's exactly right. So what we have here is what is called a 2-layer feed-forward network. Feed-forward because all information flows in this direction, assuming that that direction is forward. And it's 2 layers because you have, well, it's really 3, but you don't talk about the input as a layer. There is the hidden layer and there's the output layer. So you have input being processed into the hidden layer. The hidden layer gives features for the output layer. Now, I think probably the right way to think about this is the hidden layer is actually reorganizing the data, reorganizing the input points into a better representation so that the output is linearly separable. We know that the models, the linear classifiers are basically not going to really work well if your data is not linearly separable. What does that mean? If the features for the linear model are not good enough. So we can think of the hidden layer as something that takes inputs and transforms them into what is hopefully linearly separable. Questions? Yeah.
How does additional layers affect the amount of features that you need to start? Do you is there? It's counterintelligent this 2-layer feed, but so if we were to extend it 3 layers, would we still would there be any benefit to adding a 3rd layer with those 4, or does it make more sense if we would have more features together?
So that's so let me rephrase the question. But before rephrasing the question, let me introduce one more thing which you already talked about, which is where do these features come from, and maybe we need one more layer. maybe these features, okay, so maybe these features themselves, you don't have to invent them, another layer. So you can think of a 3-layer network or a 4-layer network or an 18-layer network, or in recent years, we see hundreds of layers in the network. And then your question is, why do I need so much depth? How does depth change anything? This is actually a question that is not entirely well answered today. There is some understanding that depth can help. Depth with limited width is easier to learn, or it kind of gives you better control in some sense. But these are all these explanations require more assumptions than are comfortable. What seems to be undoubtedly true is that it works. So if you want something to spend the next 5 years of your life, you could do a PhD on why depth is important. No, seriously, it's an interesting question and not very convincingly answered. Now, just one more point to note is this thing here, where you have a single set of weights, basically a dot product with the weights followed by this sort of a nonlinear transformation, in this case a threshold, is typically referred to as a neuron. And in this picture, there are 5 neurons. There is 4 hidden neurons and 1 output. Let's try to formalize this. Okay, neural networks more generally are perhaps one of the most, at least if you take today's mythology to heart, it's perhaps one of the most robust ways of approximating discrete and continuous functions. They are today one of the most dominant sets of hypothesis spaces that are used. It seems to work especially well for data that is, loosely speaking, human generated in some sense. The data there where we can't really think about what are good features. I don't know what a cat is. I don't know what cat features are. So let me learn that problem, and so on. Now, there are many reasons for why you keep hearing about neural networks today. Definitely one of them is that there's an obscene amount of media buzz, but there are also some underlying good ideas that you should really take to heart. One of the key ideas that seems to be that powers a lot of this is the idea of backpropagation. The backpropagation algorithm is an efficient way to essentially mechanize learning, and it seems to be it has shown to be quite useful and effective for tasks like image recognition, optical, a lot of computer vision problems, starting to see natural language processing, and so on. So, of course, so at least some of you know about biological neurons. This is a drawing made by Santiago Ramon et Cayal. He's the first one to draw by hand brain cells and discovered this really cool structure of these filaments going out of the center of the cell. And you can think of it consists of these parts called axons and dendrites, and some of you may actually know about this stuff. Definitely, if you know about this stuff, you know more about it than I do, because this is the last I'll talk about it. Artificial neurons are loosely inspired by biological neurons, and I want to emphasize the word loosely here. There are many fundamental differences. Don't take anyone who talks about emergence of intelligence because I have a neural network. Don't take them seriously. They don't know what they're talking about. So this is all I'm going to talk about biological neurons. This is pretty much all I know about biological neurons. Let's talk about artificial neurons. These are functions. These are really mathematical objects that loosely mimic biological neurons. All neurons roughly consist of the same set of parts. There is something that accepts inputs. In other words, a vector goes in. The neuron internally consists of a set of weights. So this vector is multiplied with those weights, so you get a dot product, so you get a number. And then that number is transformed. Typically, that transformation is nonlinear. So what you have that the transformation is also, it's called an activation. So what you have is the output of the neuron is an activation applied to the dot product. And for this part of the class, I will be explicitly writing the bias because this seems to be the convention in this community. So what we have is a dot product that is transformed. So this together constitutes an artificial neuron. This is what, there are variants of this, like I said, many of these things, none of these things are frozen in stone, everything is up for grabs apparently. So this is like the simplest artificial neurons that we see. This is a cartoon picture of that, you have a dot product, and this operation that we've been using all this while for SVMs and perceptrons and all these things, now taking the sign of a real number, it's called the threshold activation. It's this function. You take an input, and if it is less than 0, you call it 0. If it's more than, well, there is no line there. If it's more than 0, so if it's more than 0, you output a spike. You output 1. So this is called the threshold activation. It's just one of many activation functions. So this is really so other activation functions are possible and definitely more used than just this. I have just a small list of these things here, and this is for the purpose of this class, this is all I'll talk about activations. Perhaps the most commonly used one is the sigmoid activation function, which we've seen before in logistic regression. So you can think of the logistic regression as a sigmoid neuron. Another activation that shows up, which is the sign, this is the threshold activation. Another activation that seems to be extremely common lately for all sorts of interesting reasons is called the rectified linear unit. It's something that, so I'm going to draw pictures of each of these. The linear activation is basically no transformation. It's a function that takes the input, the dot product, and just outputs the dot product. This is the thing that you want if you want to build a regression, for example. If you want regression at the top, your output layer should have a linear activation. It may look something like this. I can't draw a line. There. Okay. The threshold, you just saw that it looks something like this. The sigmoid is something like that. The rectified linear unit is something that is 0 on all sides when z is negative, and it just gets linear on the other side, so it's still non-linear. And the tan h is basically just a sigmoid that has been expanded a bit. And there are other activation functions that have other interesting properties. You can have a sine or cosine. You can have a sinc function. You see the Gaussian, you see polynomials, and it's a huge cottage industry. But most of the time you'll encounter one of these 5, and so you should be familiar with what they are. In particular, once you see an activation function, you should think about how to take the derivative of that activation function, because that's the operation that we will need for training. And that's why the sigmoid activation, the threshold activation function is hardly ever used except in special cases, because that function is not differentiable. Any questions about what a neuron is or what activation functions are?
Professor, I'm really having a hard time understanding how it's going to pick the features correctly at first.
You and me. It turns out you're going to leave everything to learn. You're going to write down, once we come to learning, what we will see is, so this is a good question, by the way. So the reason I laugh is because I don't know the answer. It's a hope that learning works. At this point, we are asking learning to do a lot for us, the learning algorithm. So the question was, I can say what I want. Yeah, sure, that feature number 2 is actually trained by the classifier. I could want what I want. How do I know that it's going to do the right thing? The answer is, what we will do is we will define a neural network. We've still not defined it formally. We'll define a neural network and ask the learning algorithm to find the correct set of weights so that everything works out. It is perhaps entirely likely that the features it found are A, lousy, or B, humanly meaningless, if that's a phrase, yeah, humanly uninterpretable if you want, or some combination of these two things. One idea that seems to rightfully or not pervade is that all that matters is the final prediction. I don't care about the features. I don't think that's the right idea, but I don't think it's a great idea, but it seems to exist. So what you do, what you see a lot of is what is called end-to-end training. You write down a loss function in terms of a neural network. Keep in mind, the neural network is just a function. You write down a loss function in terms of the neural network, you give it to your stochastic gradient descent optimizer or some variant of that, and you hope that everything works out. And if you have a lot of data, a ton of training data, everything seems to work out, which is kind of cool. Yes?
So just to make sure I'm understanding, so we're using, you should use a neural network when you're not able to explicitly define features. Like our other ones, what we pick is features. It's really dependent on the performance of the algorithm. This is more of, okay, we're not really sure what to pick, so let's just see if this works.
In some sense, yes. So this is a good point, right? If you know that this task has these features and nothing but these features, if you are an expert in the domain who knows the domain so well that you know the features, there's no reason to add the complexity of a neural network because it goes against Occam's razor. So you should not do that. If you know the right features, of course you should use the right features and try to solve the problem. Now, if you have no idea what the features are, perhaps then you should either think about getting a neural network or maybe you want to invent some features. The pendulum seems to have swung in the direction of let me throw it at a neural network and see what happens. But it turns out you need a lot more data for that, as we will see, for training these things, because you'll see in a very shortly that these models can be extremely expressive, which means they have huge VC dimensions, which means they are extremely data hungry.
So in forms of like the cat competition, right? I mean, we're all pretty familiar with words and how they affect use. So a neural network in practice wouldn't make as much sense as.
So that's an interesting open question. We are all familiar with words and how they affect reviews, but maybe you don't know all the words that exist. Maybe some words have subtle shades of meaning that just using the words as features are not capturing. So maybe there's more to the data than what meets the eye, and we are hoping that the neural models will pick up on those signals. And that's why, for example, today the data set for the Kaggle computation, the sentiment, right? Yeah, movie sentiment. The best models for that are actually neural networks. Google internally uses neural networks for machine translation. All Google Translate is powered by a neural network. A lot of applications that you actually encounter seem to be neural networks. Maybe you don't recognize it. All these Hey Siri or Google, the voice activation stuff, the speech detection is done by a neural network because we don't seem to have perfect features for what speech is. So neural networks seem to generalize across different kinds of input pretty well. But yes, if you know the features, why not use them?
Is it something more intelligent than just sort of like reinforcing through weights and features, or is it just kind of doing a lot of those computations until it gets the right answer?
Hold on to that question. Let's get to that question when we talk about learning. There might be something more, but the naivest version calls for nothing more than that. All right, so let's actually see what a neural. Yeah.
Are neural networks ever used as like a pre-processing sort of a thing?
Oh yeah.
What kind of features do we get?
Right. In fact, it's this is a very cool thing. Like so, there is a competition in computer vision called the ImageNet competition, where there are 1,000 categories of images, and you have to look at an image and decide what object is in the thing in a picture. And there is a certain neural network called the VGG network. I forgot what it stands for. From UK, which at some point was at the top of the leaderboard. Someone did something very interesting. They took the VGG network, and so the VGG network is a neural network that looks maybe something like this. Let's say it looks something like this, with a lot more layers. What they did was they took the image, fed it in, and instead of looking at the prediction, they looked at the penultimate layer, at the state of the penultimate layer to see what features show up. And then they threw it at other image classification tasks, and it seems to be that the VGG penultimate layer gives really robust image features for a wide range of image classification tasks, which is really cool. So it has become a default pre-processing step for image classification for those who don't want to actually think about the image. Alright, so let's look at what a neural network is. Formally, a neural network is a function. It's a function that maps inputs to outputs. The outputs, for the purposes of this class, let's say the outputs are either a bit, namely it's a binary classification, or it's a real number if you have regression. This function is completely specified in terms of a directed acyclic graph. The nodes in this graph are called neurons, and they tend to be organized in layers. So you can, if you want the picture, it might look something like this. And the edges are all directed. They carry information from one node to another. All the edges are associated with weights. Any directed acyclic graph of this kind is called a neural network. It's not enough to have just the nodes and the edges. You need to have all the weights, and you need to specify for every node what the activation function is. So every node here is a neuron, which means it comes with a set of weights and an activation. The neural network is completely defined by three things. It's defined by the structure of the graph, how many nodes there are, how the graph is connected, namely how the nodes are connected to each other. One thing to keep in mind is you cannot have cycles. It has to be an acyclic graph. The other thing you need to specify the neural network is what the activation function on each of these nodes are. And then you also need to specify what the weights on all the edges are. Now, the first two components together are typically, namely the structure of the graph and the activation functions, are together called the architecture of the network. Usually, almost always, actually, I have not seen a counterexample, almost always, let's say, this architecture is predefined. Meaning, you would, if you want to invent a neural network, what you would do is you would first think hard and come up with an architecture that's just right for your problem, and leave the learning algorithm to figure out the last thing that's left, namely the weight. So the job of learning, when it comes to learning neural networks, is the edge weights alone, and the architecture comes from some understanding of the problem. Okay, now there must be questions, so I'll wait. Yeah.
Are there any rules on, as you move through layers, if you can increase or decrease nodes, or is it? So
Yeah.
like on your input pin, you go from 5 to
Oh yeah, so there are no such rules. There are no such rules.
Okay, so you could go from 5 to 3 to 5 again.
You could go from 5 to 3 million to 5 again.
Sure. Okay.
But there is also some common sense that comes in. If you go from 5 to 1 to 5, you lose information. There's no reason to go back to 5 because you essentially compressed it into one bit, or depending on the activation, one number. So there is some sense of what some common sense ideas, but typically, but not always. Typically, as the layers go ahead, the number of neurons decrease, and the idea is that you are essentially compressing the information. But these are all vague ideas, so I don't want to necessarily formalize that. So usually what happens is activations are not chosen on a per node basis, but on a per layer basis. There is some vague insight that goes in. Let's talk about the output layer. The output layer activations, we really don't have a good. We don't have a choice. If you have a classification problem, you have to use something like a sigmoid. That's pretty much all we can do, right? Sigmoid or tan H or maybe threshold. On the input layer, we don't get to choose anything because we don't get to control it. The hidden layers, every layer tends to be the same activation usually, so there's no reason for that, but just a convenience. And beyond that, there are no rules. Today, one of the most common activation functions that are used is the rectifier network, because it has interesting mathematical properties. But there are really no rules. I mean, this is one of the reasons why neural networks are such a beast to comprehend. All bets are off. Anything you want to try, go for it. If it works, then it works. If it does not, then you try again. And that's it gets to a point where it's kind of unscientific. But there are some principles. For example, rectifiers seem to be a good thing because they actually, when you take the gradient of a rectifier, the gradient does not vanish. The gradient does not become zero. If you take the gradient of, think of something like a straight line or a tan x. The tan x is a function that may look something like this. In this region here and this region here, the gradient is almost zero. So the gradient information vanishes if you use things like tan h's and sigmoids. So there's a reason to not prefer them as much. If you have an intuition as to a certain node behaves like a gate, meaning it has to be 0 or 1, but you can't do a hard threshold, then you use something like a sigmoid. Otherwise, my suggestion is otherwise go for a rectifier. Again, no bets, no formal answers, but just suggestions, guidelines. Yeah.
So it mentions connectivity there. Is there any case where we're not going to like connect each other to all the next layers?
Yes, definitely. An important example of that is a convolutional neural network, where you have essentially a convolutional neural network, some nodes are connected to this one, maybe this one, these three are connected to this, and only these three are connected to this, and so on. So convolutions, especially, convolutional networks are a very restricted, have restricted connectivity. Yes.
So you mentioned the rectifier activation layer. What is that?
Oh, the rectifier is just a max of 0. So it's this thing here. The rectified linear unit. Yes.
How does the scale, like the VC dimension, change when you scale based on depth versus based on width of the unit? So like the number of nodes?
Hold on to that question. I'll get to that maybe in 5 minutes. There are a lot of questions, so I'll get to that maybe in 10 minutes. Yes.
Going back to connectivity, so wouldn't the only difference between using, say, all 5 nodes there instead of 3, wouldn't the learner ideally just set the weights to the 2 that you don't use to 0 if that's the truth? Like, why limit?
Why limit? Okay, that's a very interesting point. So let me just rephrase the question. Mark, you asked me why, can we have examples where connectivity is not fully connected? This is called a fully connected network. And I said, yeah, you can have convolutions where the connectivity is restricted to some local context. And the question that comes up is, why bother? Any self-respecting learner would know that those weights should be 0, so it would set it to 0. Why bother with this thing? And the answer is, this is a way in which you can actually introduce some domain knowledge that you have. Let me give you an example. So let's say that you have an image. Okay. Now, what I would like, some intuition tells me that in this image, I want to capture some notion of edges that are moving. Let's say you have some object here, and I want to capture some notion of edges. What I would like to do is train a neural network that takes this image and produces an edge map, let's say. I know that in order to understand what an edge is around this area, the information in, say, this area is irrelevant. So what I would do instead is I would build a neural network that has essentially a sliding window. So I have a window over this, and I have a network that connects to this with a single node. I have the same network is just moved all around the image, and the idea is that you only use local information. And if I know that it has to be local, then why unnecessarily make the learning hard? That's intuition. Why bother? Why strain the learner when you already know some information? Yeah.
So here, what we did for path learning.
Uh-huh.
You just like go to intuition. There's no.
That seems to be. This is.
So there's no way to deal with like complexity of your.
There are some formal theorems about the complexity, learning complexity, and VC dimension, and all these things. What's happening is that, keep in mind, the VC dimension, all these learning theory results say that if you have these many examples, then you can have a classifier that is most likely good enough. It does not say what happens if you don't have those many examples. For neural networks, that number is huge, and yet we don't have those many examples, and yet we seem to have good classifiers.
So that's the confusing thing.
Right. That's the confusing thing. What's happening is really our theory is not powerful enough, it seems, to explain why these things work. Our theory says that in the limit these things should not work. Or our theory says that we need a lot more data than we have for these things to work, and in practice that doesn't seem to be happening. So one interesting open research question is asking, is there a new theory of learning that explains how and why these things work? Other questions? Yes?
So the way I see it, right, with ReLU, we kind of tend to prioritize a positive output after the application. Right? So is that kind of telling that a positive weight is a sign of enhanced feature learning and a negative weight is a sign of not learning feature well enough?
I don't fully understand what you're saying. So
let's say like all the weights are negative, then the final output is going to be negative.
oh, sure. Yeah, if all the weights are negative, then the thing will get clamped to 0.
Yes.
Yes.
So would that kind of mean that negative weights is?
That means that if all the, not quite, what if the inputs are all negative? Right? So that suggests that it likes inputs that are negative to be moved forward.
But then the ReLU would have it out.
No, so just to let's create some space. So your rectifier of some example, which is a vector x, is defined to be max of 0, something like this. Your question is, what if all of w is negative? Then if w's are negative, your argument is this whole thing becomes 0. But my counter argument, okay, w and b. My counter argument is that's not true if all x's are also negative. If all the x's are negative, this whole thing becomes positive. What that means is that particular rectifier likes to propagate information about inputs that are negative. So if it turns out that your features are of that kind, then this particular rectifier would recognize such inputs.
So images and stuff, right?
Oh, you will get negatives because the inputs are typically normalized to be 0 mean. You will get negatives. In the interest of time, I'm going to move forward and you can keep asking questions as we go along. I have to talk about the history of this thing. This is like you hear about neural networks now, but had you been in grad school in the 1980s, let's say, you would have heard about neural networks. Had you been in grad school in the 1990s, you would have been told, don't talk about neural networks, they're bad. And so on. They keep coming and going. This is a very small history, and Jürgen Schmidt has a much more detailed overview. The short and biased history goes like this. In the 1940s, Macaulay and Pitts showed how you can have linear threshold units to calculate. You can use that to simulate logic. You know that now because you know that how you can do conjunctions and disjunctions with linear models. Hebb in 1949 suggested a learning rule that has some biological plausibility, and we've seen a variant of that when we looked at least mean squares regression way back. In the 1950s, 58, 59, Frank Rosenblatt proposed the perceptron algorithm for a single layer threshold neuron. Of course, we didn't look at it that way when we saw the perceptron, we just learned a linear classifier. And then there was this huge hype about neural networks. You would see articles in the New York Times about how neural networks are going to save the world. Until Minsky and Papert wrote this fantastic book called Perceptrons, which basically killed perceptrons. Among other things, they pointed out, look, the perceptron is nice, but it can't even do the XOR. It can't even match XOR. And suddenly, the people were like, it can't do the XOR. Of course, that's not how they put it in New York Times. So the interest died down a bit. And then in the 1980s, things got more interesting again. This time through a more, from a different perspective. 1970s and 80s, Jan LeCun and Fukushima, they came up with this idea of a convolutional neural network by studying the eye of a cat. Not a cat, but cats. Also, another thing that happened was this algorithm that we call backpropagation took shape. Of course, it was not invented in the 1980s. As we will see on Thursday, it's basically another name for what is called automatic differentiation, which had existed long before. But in the context of neural networks, it turned out that this made life interesting. And then things got less, they got less popular in the 1990s because things like SVMs and such things became more prominent. And the neural networks were pushed to the background, partly because all of this was nice, but nothing seemed to work. The algorithms were there, the ideas were there, nothing seemed to work, so why bother use them? Until about 2003 or so, when something very interesting happened, namely the internet gave us a lot of data, and suddenly these neural networks started working. And also a lot of compute. So now you could do parameter exploration and hyperparameter exploration more efficiently. So a lot more data, a lot more compute. And the networks got bigger, and suddenly these ideas from the 80s and before started to show some results. There is some lesson in here about, there's some lesson in here about persisting with ideas. If you really believe in something and you have some reason that it's going to work, you should kind of build a career out of it, but that's neither here nor there. All right. So one question that comes up is, what kind of functions do these things express? A single neuron with a threshold activation is basically just a linear classifier. It separates in the space of features. It can draw a hyperplane and say one side is positive, the other side is negative. Two-layer neurons with threshold activations can draw convex shapes in the feature space. So it can say that everything inside this is positive, everything outside is negative. In general, you can have convex polygons, polytopes. 3 layers with threshold activations can give you unions of convex polygons. This is a nice picture from this textbook by Shai Shalif-Schwartz and Shai Ben David. If you want to know more about the theory of these things, I know that many of you asked that question. I strongly recommend that book because it gives some very cool theoretical insight and summarizes a lot of work. So 3-layer activations can give you, 3 layers with threshold activations can give you this. In general, neural networks are called universal function approximators. There's this classic result of Sarbenko from 1989 that says that any continuous function can be approximated to arbitrary accuracy using just a 2-layer network with sigmoids. 2 layers meaning one hidden and one output. One hidden and output can be real numbers, a linear activation. Anything can be approximated. There is a catch there. The catch is that the hidden layer can be might end up being huge. It might end up having a huge number of neurons. There was some work from the early 90s that said, your choice of activation functions, the answer to the question that came up, maybe your choice of activation functions is not that important. If all you care about is approximation, you can kind of do reasonably well. Something that you should be able to prove using what you've seen in this class is that any 2-layer threshold network, any Boolean function can be expressed as using 2-layer threshold networks. I strongly encourage you to prove that. The question about VC dimensions came up. Roughly, the VC dimension of a neural network is something like the number of edges that are in the network. So if you have a threshold network, then the VC dimension is in the number of edges times the log of that. If you have sigmoids, it's something like the number of edges squared. So the short, oh, by the way, if you have only linear units, then having multiple layers makes no difference. Try to think about why this is true. So the brief summary of all of this is that neural networks are extremely expressive. There are standard results from the 80s and the 90s that show that neural networks can capture any Boolean function, it can capture any real valued function. All of them come with a catch. The catch is that that network that captures any Boolean function might end up being extremely wide or extremely deep. From the 80s, it was all about wide, not deep. The problem with that is that the VC dimension, the learnability of such networks is extremely hard because the VC dimension, or at least according to the theory that we have studied so far, such networks can be extremely hard to train because the VC dimension of neural networks is roughly of the order of the number of edges, the number of edges squared or something like that. So as the networks get harder, sample complexity gets more. As the network gets larger, sample complexity gets higher. It doesn't matter if it gets larger by making them deeper or wider. So neural networks can be hard to train if you make them extremely deep. Of course, that doesn't agree with everything that you see in papers today, because you have 150 layer networks that are extremely wide that seem to work, and that's where the question about why this theory is not completely sufficient comes up. Okay, so what we've seen so far is, all we have seen so far is what neural networks are. On Thursday's lecture, we'll look at how these things are used for making predictions, and then we'll come to the backpropagation algorithm and talk about how they're used for learning, and we'll get to some practical issues, most likely at the beginning of next week. All right, I'll stop now. Don't forget your homework and such things, and there is that cool talk from Gordon today, and I have office hours at 4 o'clock. I wanted to respond to you last